My name is Professor Orata, and we are continuing with our lectures in thermodynamics. So today we look at phase equilibria. Phases are very important in the sense that, we have the three phases which you are familiar with. That's the solid, liquid, and vapor phases. And so these transformations involving these phases are fundamental in thermodynamics because most of the processes involve phase transformations. So for example, if you have water being converted to ice, you put your water sample in a deep freezer, convert it to ice, and this particular process, here we have liquid, and here we have a solid phase. And notice that this particular transformation from liquid to solid does not result any change in the chemical constitution of the sample. In the same way, if you heated the liquid to the gaseous form, the vapor, yes, there's a change in the phase from liquid to vapor, but there is no change in the chemical constitution of that particular sample. We still have H2O. And these are familiar processes. We know that process, that is freezing, and this is vaporization. So as you have mentioned in earlier lectures, we have enthalpies associated with these phase transformations. We have those enthalpy values. For example, that will be enthalpy of vaporization, and that will be enthalpy of fusion or freezing. So, and of course, the enthalpy change we have already seen in thermochemistry, one of those lectures in thermochemistry, how we compute these particular enthalpy changes. Now, we have said there are three phases which are characteristic of matter. We have the solid, the liquid, and the vapor or the gas phases. Now, the key question is, in terms of a thermodynamic sense, what makes a particular phase be stable under ambient conditions? That is, existing conditions, whatever your conditions. Why, for example, would liquid water be stable at STP under ordinary conditions? Why, for example, will above 100 degrees centigrade the gaseous form of water be the stable phase? Or why would ice or solid water be the stable phase below 0 degrees centigrade, for example? So there must be a thermodynamic explanation for this phase stability. And the key determinant here is what we call the chemical potential. And this chemical potential, we denote it as mu. So remember, don't confuse with in other lectures in thermodynamics where we talked of mu JT, which was Joule-Thomson coefficient. Here we are just saying the chemical potential, the notation is mu. And the chemical potential derives from the Gibbs free energy, G. Derives from the Gibbs free energy, G. Now, G, that is the Gibbs free energy, is a state function. We have already mentioned this in earlier lectures. And state functions, we said, depend only on the state of the system and their exact differentials. So it means that if we take G as a function of temperature, pressure, and quantity, then being as an exact a state function is a state function, and by extension, an exact differential. Therefore, we can write the total derivative for G as dG is equals to del G, del T, P, and N kept constant, dt, plus del G, del P, T and N kept constant, dP, plus del G, del Ni, the Ni, T and P kept constant, and that is summed over the number of chemical species. And that molar gives free energy, or this quantity, which is a partial property of that function, is what we call the chemical potential. That is the chemical potential. And its change with temperature here will give us what we refer to as the molar, that's the entropy, minus entropy. S is entropy. You are now familiar with entropy. We have talked a lot about entropy, especially when we are talking about the Rankine cycle and the Carnot modified into the Rankine axis. And that is the entropy, and this is the change in volume. In a nutshell, what are we saying? Del G by del T. That is, let's remove the constraints. dG by dt is equals to minus S dG by dP is equals to volume, and we have our dG by dN as our chemical potentials. And remember, like we had said in earlier lectures, once again, when we dealt with partial derivatives, like when we talked of del U del T and a constant volume, which is succoric heat capacity, or del H del T and a constant pressure, which is a subaric heat capacity, we talked of del. Del means that we keep one or more variables constant during the change of another. So I've freed these ones, I've removed the constant elements there, so that I've crossed over from del to D. Remember that we said is del and stands for partial derivative. Now, in the same way, like we have seen, we can also denote this quantity as G bar. G bar as being G over N. And we are going to use that. So we are going to work with this towards the end of the lecture. So just make sure you have kept in mind the things I've talked about. So we have said the chemical potential determines the stability of a state. In other words, the phase with the least chemical potential is the stable state, is the stable phase under those conditions. That is, the phase, stability of a phase, let's note that, depends on the chemical potential. So that if water is the stable phase under STP, then it means that if water is the stable phase, that's the liquid is the stable phase under STP, then the chemical potential of the liquid is less than the chemical potential of the solid, and is also less than the chemical potential of the gaseous form. If we are at above 100 degrees centigrade, so that water vaporizes from liquid to vapor, then in that particular case, the chemical potential of the gaseous form of water will be less than the chemical potential of oil. That is, let's say for water, above 100 degrees centigrade, then the chemical potential of the gas phase, the water, will be less than the chemical potential of either the liquid or that of the solid. And you can illustrate this graphically so that you get the gist of this information. Let us look at it, illustrate it graphically. So let's say at STP, so we have the chemical potential so that we are saying under ordinary conditions, the chemical potential here for the liquid will be lower than the chemical potential. Chemical potential of the solid will be lower than that of the liquid, which in turn will be lower than that of the gas. So let's call the solid S, the liquid L, and that of the gas. So clearly you can see that under normal conditions for water, let's say that's for water, H2O, the chemical potential of the solid phase will be less than that of the liquid and that of the gas. So if you extend that, you can see that definitely that of the liquid is higher than that of the gas is higher than all of them. Now, the point at which the two chemical potentials of those phases are equal, then it means that those two phases are coexisting in equilibrium. So that we have at this particular point, that is, solid and liquid coexist in equilibrium. And this corresponds to the freezing point. And where we have the liquid and gas coexisting together in equilibrium, that corresponds to the boiling temperature. Or the temperature at which the liquid vaporizes. Is the temperature at which it freezes. Now, we have already said that if we change in chemical potential, when you change the chemical potential by lowering the pressure, remember in the elements of science and engineering, we know that when you lower the pressure, then it affects the boiling and it affects the freezing points. So if we lower the pressure here, let us lower the pressure of the solid. That line representing the solid will drop down, and that representing the liquid will also be lowered. And that now corresponds to a new temperature, let's call it TF prime. And you clearly can see there's a lowering in the freezing point. If we repeat that also by lowering the pressures, then we are seeing that we are going to lower the boiling temperature. TB, boiling temperature. So when you lower the pressure, it affects the boiling and freezing temperatures. And that we know the reason from elements of science and engineering. Now, when we are dealing with these phases, it is very important to know that we need to know what is a phase. Phase basically is a state of matter which is uniform throughout. It's a state of matter which is uniform throughout. Uniformity. And that's why, for example, if you mix water and ethanol, you will have a homogeneous solution. It is uniform throughout. But if you mix two substances which are not miscible, then they will separate. then there will be a separation of phases. We will have two phases. For example, if you mix paraffin or kerosene or paraffin oil with water, they're going to separate. So you'll have two phases. So they are not, that's not a homogeneous phase. So we'll have two phases. So when you're talking of a phase, that is, we are talking of uniformity throughout that system that represents our phase. And component is the minimum number of independent species which you need to describe completely the composition of that particular phase. So we denote that, we can denote that as P, and we can denote the component as C. And so determination of components is not as simple as being able to tell whether we are dealing with a homogeneous phase or a heterogeneous phase. We look at it just from quick visual score. You'd say this is a uniform phase. I've mixed water and I've mixed with ethanol. Bingo, uniform. It's not as simple as that for components. For components, you have to worry about a few things. To determine the number of components, you need to know the number of species. For example, ions which are there, etc. And the relations. For example, are we having electroneutrality? Are we having equilibria? And so forth. Equilibrium, etc. So for you to determine phases, you cannot just say components, that what is a one component system. You need to be able to show in terms of the species which are there, and in terms of whether there's electroneutrality or whether the components. So you will think of water, there's H2O, there's OH, there is H+, those are species which are there. Is there equilibrium between them? For example, H2O breaks down into that plus that to OH. That's an equilibrium relation. And is there electroneutrality? Yes, there are charges there. So you put them there and you are able. You put all those species which are there, you subtract from the number of relations, and that will give you the minimum number of independent species which you need to describe completely the composition of that particular system you're talking about. So it's very important to note those kind of things. And of course, you can do a few of those. You can think of, for example, if you took phosphoric acid, the number of species in phosphoric acid will be phosphoric acid itself, there will be H2PO4 minus, there will be HPO4, double charge, there will be PO4, 3 minus. And so you can see that already there are many species, and all these species coexist in equilibrium. There is H3, we will have H3PO4, coexisting equilibrium, H2PO4 minus plus H plus, and you can continue those systems. Then you'll be able to compute what are the number of components in your system. Now, it is very important for us. It's very important for us to be able to determine the profile of a pressure temperature diagram, which is the axis on which these phases are normally illustrated. For example, you know that if you take, for example, for carbon dioxide, that is the phase diagram for carbon dioxide. We have the solid, we have the liquid, and we have the gaseous phase. That is for carbon dioxide, this pressure temperature. That's pressure temperature diagram. Now, let's see if this one is clearer. Pressure temperature diagram. That is for carbon dioxide. But when it comes, for example, to water, if you come to water, the pressure temperature diagram for water, we have that profile, solid, liquid, and gas. Pressure temperature diagram. Now you can clearly see that in this particular diagrams, this is for water. They look alike, but they are not alike. For example, we have said Along this boundary, solid and the liquid, along this boundary here, solid and liquid are coexisting together in equilibria. This particular boundary here, solid and gas are coexisting together in equilibria. And here we have liquid and gas coexisting together in equilibria. Along this curve here, we have again solid and liquid coexisting together in equilibria. Liquid and gas are coexisting together in equilibria. Solid and gas are coexisting together in equilibria. So this process is melting. That process is vaporization. Now, we can have that process from solid directly to gas, which we normally call sublimation. In other words, when you lower, for example, the pressure of the system, you can lower it to a point where now there is intersection between the curves for the chemical potential curve for the solid and that of the gas before it intersects that of the liquid. In that case, you'll have sublimation, the kind of diagram we have spoken about just a few minutes ago. Now, in these systems, that is the triple point. This we call the triple point. And at the triple point here, the solid, liquid, and gas coexist in equilibrium. This triple point is invariant. We are going to see it in subsequent lectures when we talk about phase rule, that the number of degrees of freedom at that point will be 0. And we'll be able to show that from phase rule, which relates components, the number of components, the number of phases, and pressure temperature variables to give you what we call phase rule, which is F is equals to C minus P. We'll come plus 2. C minus P plus 2, that is called the phase rule, and we are going to come to it in the next phase rule. We are going to come to it in the next lectures. It's very important in terms of handling these phase diagrams. Now, again, the same story is here. That is the triple point. And this triple point, because it doesn't change, let's just mention it. The triple point doesn't change. In other words, you have no degree of freedom at all. If that is the pressure, that is the corresponding temperature, no other. So it is fixed. It's not like in this region, say, for example, solid, where you are able, if I pick this point, I will still have a solid corresponding to P1, T1. I pick this point, I will still have a solid, P2, T2. In other words, the variance for that system in the single phase there, because this is a single component system, is actually 2. So I can play around with pressure, temperature. It's actually, let's see, single component system, 1, phases are, phase in that system is 1, and then we have 1 component in this particular case, and we are talking of a single phase there, and we have plus 2. So it's telling us that we have F is equals to 2. So it means I can vary pressure and temperature as I wish. When I go to triple point, where we have 1 component, carbon dioxide, I have 3 phases, 1, 2, 3 in equilibria, plus 2, then it is 0. It means I have no choice. That is the triple point. That is the triple point. But if I go in the region where there are 2 phases in equilibria, like in this region here, then you will see that at that particular point, F is equals to 1 component for the system, and there are 2 phases plus 2, so I have 1. So I can only choose, I have only 1 degree of freedom. In other words, if I pick the region where we have solid and liquid coexisting in equilibria, that is this curve here, if I pick this pressure here, I have no choice. That is the temperature. I can only pick the pressure, but I cannot pick the temperature. If I pick the temperature, I cannot pick the pressure. That's the pressure. And we are going to see that in subsequent lectures when we come up with the phase rule and look at it more in depth. Now, this is the pressure temperature diagram. So it becomes very important for us to derive the Clapeyron equation, which is for these pure substances, and is very critical in construction of those phase boundaries which you have shown there. They are very important in the construction of phase boundaries which you have shown. The Clapeyron equation is important in the construction of these phase boundaries. That is look at the Clausius-Clapeyron equation. Now, if we take a pressure temperature diagram and we say that we have phases alpha and beta coexisting in equilibrium, and we focus on the state point, let us focus on the state points 1 and 2. State points defined by that pressure, let's call it P1, T1, and this other one will be defined by some pressure differing from this one by some infinitesimal amount. We have already talked about infinitesimal quantities when we are talking of D, and we have talked of measurable quantities when we are talking of delta. And so we are saying, let that be T2. Let that be T2. Now, so we have pressure P1, we have pressure here, let's just call it P, P1, T1, and P plus dP, and then of course this is also T plus dt. Now, one of the first things, that's why I said keep this in mind, we have already seen that particular expression. Now, for pure substances, like I had already indicated earlier on, G bar is G over N. And that is the molar Gibbs free energy, which is the chemical potential, so that if we rearrange this quantity, G is N G bar. So if we take the total the derivative of this G, we get N dG bar plus G bar dN. So I've just used the product rule. The mathematical identity which I've used is D of Ux UV is equals to U dV plus V du. In other words, if you're taking the differential for a product, it is simply U dV plus V du. So in the same way, you can think of that as U and that as V. So you get U dV plus V du. I've just used the product rule. That's a very important mathematical identity. These are things you should familiarize with. Quotient rule, you need to know the integral calculus. They are very important in thermodynamics. You need to know about the series. Become very, very useful in thermodynamics, especially for statistical thermodynamics. Then the series are normally very important. Now, we can equate these 2 points. So in other words, the chemical potential here, we can call it G bar 1, and that is G bar 2. So let's use now the board. This side, I think we can use this side. So we are saying that what we have is that we have this particular quantities, dG. dG we have seen is now entropy minus S dt, and this is plus V dP plus the chemical potential dN. And this is equal to, remember we have dG also as N dG bar plus G bar dN. Now, if we equate both equations, because these are the same, then we notice that this will cancel out that, so that if you add minus S dt plus V dP plus mu dN as being equal to, just remove this now so that you can be able to do some work there. N dg bar plus g bar dn. We say that is chemical potential, so that will cancel with that. So that what do we have? We now have minus S dt plus V dP is equals to N dg bar. Of course, dividing throughout, if we divide throughout by N, divide throughout by N, divide by N throughout. So very simple. We got that based on the fact that Gibbs free energy is a state function, therefore an exact differential. So if it's an exact differential, we said you can write it in that particular form. In case you have not gotten that particular lecture, is in the lecture series there. I repeat again, very important. If a function is a function of x and y, then if it is an exact differential, the f is equals to del f del x dy dx y constant plus del f del y x constant dy. And we went further to show how we can go ahead and prove further that it is an exact differential. So if you look at the lecture on alpha and kappa coefficients, that is the isobaric, that's the isobaric coefficient of thermal expansion or isothermal compression. On those lectures, we have worked extensively with partial derivatives, and we have shown the mathematical identities, that's the permuter and the inverter, which you can use to break down some of these quantities, because it becomes very useful. And these partial derivatives which we have here are not just abstract, they are real. That talks about entropy, that talks about volume, that talks about chemical potential. Fundamental, critical, because entropy, very, very critical. Delta G is very important. It's the one which determines the direction of a reaction. For example, when the change in Gibbs free energy is negative, that reaction will move forward. When you are designing your reaction, you want that reaction to have a negative delta G, so that you know that it will go forward spontaneously. If delta G is 0, that's an equilibrium reaction. It keeps going back and forward, back, forth, almost quasi-static. So that you might think that it's not moving, but of course it's moving. The forward reactions are balanced with the reverse reaction. But if it is positive, then it means that reaction requires more attention from you in terms of input of energy. You might have to pump in some energy for it to move forward. It will be non-spontaneous. And that's what we talked about in thermochemistry. If you look at the lecture in thermochemistry, it's very important for you as a professional to know what is the enthalpy change, for example, of a reaction. Is it endothermic? Is it exothermic? Endothermic, you might have to pump in some energy there. And how does it come in? We said if the enthalpy is negative, that's exothermic reaction. Heat is being released, so you must be able to know what to do. If you're using a batch reactor, you must use a continuous stirred tank reactor, for example, where you are able to lag your system and allow water to move around it to cool the system, because there could be a lot of heat generated. If it is one which is endothermic, it means you have to supply heat. Instead of cooling it, you might be supplying hot water around it to jumpstart your reaction. And these things are related, because that G you are seeing there is related to enthalpy in the form G is equals to H minus Ts. So that's enthalpy. So if you took delta G will be equal to delta H minus T delta S minus S plus S delta T. So they are related. When you look at H, it is related to internal energy, U plus PV. They are all related. They're all related in one way or the other. Very important for us to note. So we come back to where we were. We come back to where we were. I repeat, G is a state function, is a state function and an exact differential. So we have seen that these two, if we divide throughout by n, then we have minus S over n dt plus V over n dP is equals to dg bar. Now, when the two phases are coexisting in equilibrium, then dg bar of phase alpha must equal to dg bar of phase beta. We say the chemical potentials in both phases must be the same for that particular component. Now, if we now simplify that expression there, if we simplify this expression here, what do we get now? Let's simplify this expression here. So for the alpha phase, dg bar alpha will be given by, remember, I repeat, when we divide this quantity, when we divide these thermodynamic quantities by the amount of substance, they become partial molar quantities. Partial molar quantities. Remember in our earlier lectures on heat capacity, we talked of heat capacity, which was an extensive quantity dependent on the amount. But when we divided by n, it became molar heat capacity, becomes an intensive variable which does not depend on amount. So what we have now here is when we divide S by N here, it becomes molar entropy minus Sm. That's molar entropy. And V divided by N becomes molar volume. Becomes Vm, that is molar volume. So that, what do we have? We now have minus Sm alpha plus Vm alpha. We have dp and dt. I've forgotten to write that down. We have dt plus Vm alpha dp and dg bar beta is minus Sm beta dt plus Vm beta dp. Don't forget that alpha and beta were simply the phases which we said were in equilibrium. It can be solid in equilibrium with liquid. It can be liquid in equilibrium with solid. It can be liquid in equilibrium with gas, and so forth. All we are talking about are the phases which are coexisting in equilibrium. Now, if we rearrange these particular quantities, because we say the two are equal because they are in equilibrium, then since they are in equilibrium, then it means that minus Sm alpha dt plus Vm alpha dp is equals to minus Sm beta dt plus Vm beta dp. The phases are coexisting in equilibrium, so the chemical potentials are the same. So if we collect like terms together, then I will have minus Sm alpha plus Sm beta dt is equals to Vm beta minus Vm alpha dp. I have no problem. I can simplify, make my life a lot easier than talking of minus Sm plus Sm. It's simply Sm beta minus Sm alpha. So I just have Sm beta minus Sm alpha dt is equals to Vm beta minus Vm alpha dp. So the dp over dt, which is the slope of the phase diagram, is given by, that is dp over dt is equals to Sm beta minus Sm alpha divided by Vm beta minus Vm alpha, which is basically purely delta S over delta V. So dP over dt, which is the first diagram which we had, that is, when we took, for example, the first diagram for water, solid, liquid, gas, we said that was the triple point. I remind you once again, triple point. That slope is given by the change in entropy divided by the change in volume. Because remember, the axis is pressure and temperature. And this is very important. This is very, very important result. This result here is the Clapeyron equation. That is the Clapeyron equation. And that Clapeyron equation is critical. It's the one which we use in construction of these boundaries. Using the Clapeyron equation, we are able to construct these boundaries. What does that mean? Now, delta S. Let's go to delta S and look at vaporization and see how we can actually, for example, construct the liquid. The liquid and the gas boundary. Let's see how we do that. We have said that dP by dt is equals to delta S over delta V. Now, we use what is called Clausius inequality. Clausius inequality is a consequence of one of the laws of thermodynamics which I've discussed in our earlier series, which tells us that ds is greater or equal to dq over T. And we have also mentioned in those earlier lectures that heat which you transfer under constant pressure is the same as the enthalpy, and heat which you transfer under constant volume is the same as the change in internal energy. And we said that those two relationships, that is, we say that dH is the same as heat transferred under constant pressure, and du is the same as heat transferred under constant volume. Now, this is a thermochemical observable. We have talked about it in our lectures, in earlier lectures, and this is a thermodynamic state function. Dynamic state function. This link between thermochemical observables and thermodynamic state function is the heart of thermochemistry. Is the heart of thermochemistry. Very important for us to remember that. Now, if we are dealing with constant pressure, then dH is equals to dQp, heat transferred under constant pressure. Therefore, if we have this quantity here, you integrate it, we have that delta S under constant pressure here will be heat transferred and constant pressure over T, which we can as well write as delta H over T. So, we can now replace that delta S by delta H over T, so that the Clapeyron equation now, the Clapeyron equation dP over dt, therefore, the Clapeyron equation, those three dots are for therefore. So don't get confused and think that it might mean atoms or electrons in one way or the other. No, this is just therefore. I don't want to write therefore altogether. So therefore, dP over dt can now be written, I replace the delta S with that expression there, it becomes delta H over T delta V. Now, if I'm talking about the boundary between liquid and gas, which is vaporization, then that one, I will use the equation delta H for vaporization. That's the enthalpy change accompanying the vaporization process. That's the first transformation from liquid to vapor, and the temperature at which it occurs. And remember, when there are phase transformations, we have talked about that in Carnot and Rankine circles. When there's this phase transformation, that assumption that knowledge that at phase transformation, the temperatures are constant, that help us interface the Carnot cycle into the Rankine matrix on temperature entropy axis. Now, in the same way, this will be the change in volume on vaporization. And so using this relationship, you are able to generate these boundaries. You are able to generate those particular boundaries. And we are going to see how do we apply the Clapeyron equation to construct these phase boundaries. Solid liquid, you already are seeing we have enthalpy of vaporization. If we know the volume change of vaporization, we know the temperature change. Just look at it. Let's just give you a hint before we move to it at some point. If we rearrange these quantities, then we see that we will have dP. We will have dP is equals to delta H vaporization over delta V vaporization dt over T. And already you are familiar with this. Remember we said if we use the mathematical identity integral of dx over x, that becomes the natural log of x plus c, because you don't put boundaries, so we have to have the integration constant, and natural log is log to base e. Log to base e. Not log to base 10. If you go to log to base 10, then you have to multiply it by a factor of 2.303. And so we already see that if we integrate dp from some limit, let's call that p star, to another limit p, then we will have delta H vaporization over delta V vaporization integral from T star to T dt over T. And you're seeing things are becoming easy now. I can take the T star and P star as temperature and pressure under ordinary conditions. Then I keep varying them. I keep varying pressure, temperature, and seeing what I get. And that coordinate pressure, temperature, pressure, coordinate pressure, temperature, coordinate PT. Coordinates here, which I keep generating, which I will generate and generate, PX, TX, PY, TY, and so forth, are the ones which are used to construct this. So we are going to look at that in the next lectures.